Hi, and welcome to my video lecture series. This is going to be the very first lecture of the year, and so we're going to do a short introduction to geometry and mathematics, and then we're going to talk a little bit about patterns and inductive reasoning after that. So first, a little bit about mathematics in general. Mathematics has really been around for thousands of years. Early counting methods, we have evidence of that as far back as 20,000 years ago, where they would make marks in the bones of animals that they had killed to keep track of things like maybe how many goats they had or something like that. The Egyptians came along, and they were around about 6,000 years ago, and they actually, at that point, started the very first, or one of the first, actual numbering systems where they had different symbols for different numbers. And that was a first. As far as we know, we don't have evidence of any earlier number systems than that I can tell in my research. And a little bit after that, about 500 years later, the Babylonians came along, and they had a slightly different numbering system. They had what's called a base 60 numbering system. So think about, in our numbering system, we have 10 numbers, 10 different symbols for the numbers 0 through 9. Well, they had different representations to show 1 through 60. They didn't understand the concept of 0 quite yet. And so there were 60 different representations that they had to know and be able to use. We still have evidence of their numbering system today. Think about time, since there are 60 seconds in a minute and 60 minutes in an hour. And it's also evident in our 360 degrees in a circle. That is a multiple of 60 that was used. So there's definitely, we can trace back some of our roots of our mathematics that we use today to the Babylonians as well as the Egyptians. Geometry started about 5,000 years ago in Egypt, when they had to come up with a system. Whenever the Nile River would flood, they had to figure out how they were going to give the same amount of land back to all of the people, the same amount of land that they had before the flood. So they would measure the land and keep track of that, and then after the flood, they would go back and measure again to make sure that people got the same amount of land as that they had before. So geometry, think about the Great Pyramid of Giza, was built around 2600 BC, which was quite a long time ago. And you know, that was quite an accomplishment by a civilization that long ago. So moving on, some of the others that are kind of important to us. Pythagoras, we'll talk about Pythagorean theorem later on in the year. But Pythagoras was actually the head of a group called the Pythagoreans, and they made a lot of contributions to mathematics and geometry. And that's kind of what they did, is they sat around and they thought about mathematics and came up with things. And then about 300 BC, Euclid. Euclid is really probably the most important person for us in geometry. Actually, our geometry that we'll be studying is called Euclidean geometry. So he really was the first to formalize a lot of the thoughts and ideas about geometry. He started doing proofs which had not been done much before. And he really combined it all into one formalized system. So he was a very big contributor to the geometry that we're going to be studying this year. So let's start out. We will first talk about some patterns in inductive reasoning. So now is where you probably want to start taking notes. We have a definition to talk about, definition of inductive reasoning. And inductive reasoning is making a conclusion based upon observations and patterns. So for example, one thing that we might observe is the weather. The weatherman might see that a particular weather pattern develops when certain things happen. And so they might make a prediction based on the weather pattern that they see taking place. So we'll see some more examples of that here in a minute. So of course a pattern is a set of things with like characteristics. So here is an example of a visual pattern. So in the example, what comes next in the pattern? So if we take a look at this pattern, we have one dot. The next one, we have two dots connected with a line. So we may not have enough information quite yet to continue the pattern, so we'll look at the third one. Well, the third one is two dots connected with a line, and then we have a third dot. The fourth in the pattern has four dots, and we have two lines. So now you might have enough information to kind of get an idea of what pattern is taking place here. Every time we add a dot, we may or may not have a line depending on how many dots there are. So in this case, one dot, no lines. In this case, two dots, one line. Three dots, we added a third dot, but we didn't add another line yet until we get to the fourth dot. And now we have four dots with two lines. So next, we have five dots, but we didn't add another line yet. So we might be going, okay, so what is next in the pattern? That might be a question that you might see in your homework. What's next? So we might be able to tell from there that, well, we're going to add a sixth dot. And this time, since we have an even number of dots, we're going to connect with a line. And so we have three lines. So six dots and three lines. So there is an example of a visual pattern that you might see. And now we'll talk about some others. So number patterns. Find the next two numbers in the pattern. So we start off, we have the number 1, and second we have the -2, and then 3, and then -4, and we have to fill in the blanks. Well, notice that we have just the integers, and every other one is negative. So you can kind of tell the next number must be 5, and then the next number after that, we have to make it negative, and we go to the next integer, which is 6. So there is a number pattern, and you will see more of those. And we might also see some letter patterns. So complete the pattern. So if we had these 5 letters, and you were asked to find the rest, well, we have J, F, M, A, M. And so it might take a second to figure out, well, what does this represent? And so we have to kind of think about that for a second. And notice sometimes patterns can continue on forever, like this one would. Sometimes there is a terminating number of letters, in this case, to our pattern. So in this case, there are going to be 12 total, and that might give you kind of a hint as to what the pattern is. So if we look at the letters actually represent the first letter of each of the months in the calendar. So J stands for January, February, March, April, May. So if we continue the pattern, we have June, July, August, September, October, November, and December. So that completes the pattern. So you may see some other patterns, and sometimes you kind of have to think about, well, what do these, usually they represent a word of some sort, but not always. So just be aware of that. But in this case, you can see there was definitely an end to our pattern, and each letter represented something that we're familiar with. So now for another definition, a conjecture. A conjecture is a conclusion you reach using inductive reasoning. We could also call it an educated guess. So just note here, and make sure to note this in your notes, examples do not prove a conjecture. So we could come up with examples all day long, but just because we can find a lot of examples does not necessarily mean that we have proven that conjecture to always be true. And a counterexample is an example that shows a conjecture is false. And also note, it only takes one counterexample to prove that a conjecture is false. So just one. So we could find all sorts of good examples, and that doesn't necessarily prove it, but one counterexample will show that it's false. So here, make a conjecture about the sum of the first 30 odd numbers. So if we look at the first one, well, we just have one number, which is 1. So it's equal to 1, which is the same as 1 squared. The second odd sum, well, that would be 1 plus 3, and 1 plus 3, of course, is 4. And we might notice that 4 is the same as 2 squared, or 2 times 2. Our third odd sum would be 1 plus 3 plus 5, which 4 plus 5 gives us 9, which we might notice is 3 squared. So hopefully by now you're starting to see the pattern that's taking place here, so let's check it, the next one. The fourth odd sum is 1 plus 3 plus 5 plus 7. So it is just the 9 that we had before, plus another 7, which makes 16. And well, we do know that 16 is the same as 4 times 4, 4 squared. So far our conjecture seems to hold that maybe the sum is just whatever number that is squared. So we can make a guess that probably the 30th odd sum is going to be 1 plus 3 plus 5 plus 7, and so on up to 57 plus 59. And if we add all of those together, we get 900, which would be the same as 30 squared. So if you're not sure if this is really the case, you're welcome to go ahead and check. Take all of 1 plus 3 plus 5 plus 7 all the way up to 59 and make sure that that equals 900. And it should. So sometimes we do have to think about, you know, what is the pattern that's taking place, and it takes a little bit to think about that. But in this case, hopefully, once you saw the first couple in the pattern, you were able to pick it up pretty easily. So in the very last example I have today, finding a counterexample. So if we can find that one counterexample, we know that our conjecture is going to be false. So let's think about when we cut up pizzas. When you cut a pizza, there are twice as many pizzas as there are cuts. Pieces as there are cuts. So, and if you think about that, if we cut the pizza once, it cuts it into 2 pieces of pizza. If we cut it twice, well, that should cut the pizza into 4 pieces. So if we do 3 cuts, if we cut it, it seems to make sense that it should make 6 pieces. So sometimes we have to think outside the box, though. So this is the case if we cut it exactly through the center of the pizza, or all of the cuts happen to overlap at one place. But what if they don't all overlap in a single spot, hopefully close to the middle of the pizza? If we cut it something like this, where maybe we make the first 2 cuts exactly through the center, but the third cut is off to the side. Well, if we count all of the pieces that would be made, we have 1, 2, 3, 4, 5, 6, 7 pieces in our pizza instead of 6. And so that particular cut that we just made is what we need to do to come up with a counterexample for our conjecture. So what we've done here is we have found an example that makes our conjecture false, so that is a counterexample. It makes the conjecture false. And so really it is important to think outside the box when you're finding a counterexample. And even when we make a conjecture, it's easy to make a conjecture and come up with lots of examples to see if it's true, but we don't think of all the possibilities. And so when you're trying to think of all the possibilities to make sure that something is true, think outside the box and try to come up with some other way of doing things that might make our conjecture not quite work. So that's it for now. Thank you for joining me today, and hopefully I'll see you again all soon.